Kepler's third law of motion. Now we can find the relationship between any period t and the orbital radius for any orbit. Here's our orbit here, here's our velocity, and it's going around this planet or star, whatever. We have velocity, which is distance over time, which again for a circle is just the circumference over the period, or 2 pi r over t. We also found the orbital velocity earlier. That's the square root of gm over r. So we set square root of gm over r equal to 2 pi r over t. Nobody likes square roots in equations. Okay, so we're going to square both sides. Then I'll get gm over r is equal to 4, right? Square 2 you get 4, square pi you get pi squared, r squared over t squared, and that's this right here. Then we cross multiply. We multiply both sides by t squared and r. Okay, so r is going to go wind up over there, and this t squared will go over here. So we get gm t squared is 4 pi squared r cubed here. Then we divide both sides by r cubed and also by big G and big M. So we get the ratio here of t squared over r cubed is equal to 4 pi squared divided by G, the universal constant, and the mass of the object being orbited. This is Kepler's third law. This is incredibly profound. Kepler had noted through measurements now, that the ratio of t squared over r cubed yields the same result for all the planets. That is, the square of the period of any planet's orbit that is going around our sun divided by the cube of its distance from the sun always yields the same number. That's phenomenal. We've now shown why with this equation. 4 pi squared over gm, that's a constant. It's the same for orbiting objects. Notice, we don't show the radius of the object there. We don't show the mass of the object. As long as it's going around the sun, its solution for t squared over r cubed will always be 4 pi squared over gm. M is the mass of the object being orbited, in this case the sun. It is independent of the object that is orbiting. That is phenomenal. Example 1, Kepler's third law. Geostationary satellites are special cases of geosynchronous satellites. They orbit over the equator with a period of 1 day, so they are always over the same location on the equator. The moon is 60 r sub e, that is Earth radii, from the Earth's center and has an orbital period of 27.3 days. Using just the above information, determine the satellite's distance measured in r sub e from the Earth's center. We gave the moon's information because we're going to use it in Kepler's third law. We've got how far the moon is from the Earth, from the center of the Earth. Here's the period of the moon making one complete orbit around the Earth. And here's our geosynchronous satellite. It makes an orbit every day, and we want to find out how far above the Earth's center it is. So here's Kepler's law. T squared over r cubed is the same for anything orbiting the Earth. We solve for the distance of the geosynchronous satellite. Notice that's cubed, so that's going to be the moon, how far away it is, cubed, and the period of the geosynchronous satellite squared, and the period of the moon squared. So we'll group the terms that are squared. Those are the two period terms. Now we put the numbers in. Here's the distance of the moon from the center of the Earth, 60 times r, radius of the Earth, cubed. And our geosynchronous satellite has a period of 1 day, and here's the period of the moon. We then square that. We get 0.0013, and days cancel out. Then we have 60 times the radius of the Earth cubed times 0.0013. Now we take the cube root of both sides. So the distance of the geosynchronous satellite from the center of the Earth is 60 times the distance of the moon from the center of the Earth times the cube root of 0.0013. Cube root of that is 0.11. And finally, the geosynchronous satellite, to have a period of 1 day and stay in the same position over the equator, that distance from the center of the Earth is 6.6 times the radius of the Earth. And we'll have some discussion on the next page. So if we now have this satellite located over the equator at a distance of 6.6 times the radius of the Earth from the center of the Earth, it will remain in one location over the Earth, since locations on the equator also complete one rotation every day. If you look at satellite dishes, they are always pointed to a fixed location over the equator, so they are aimed to your south if you're in the northern hemisphere. Their height above the Earth's surface, however, is only 5.6 times the radius of the Earth, since we need to account for the fact that Earth's surface is one radius above the Earth's center. These satellites must be over the equator, since they would otherwise be orbiting with the correct period, but they would not be moving along with Earth's surface. Example 2, Kepler's third law. Many satellites, including the International Space Station, are very near Earth's surface. Using just this information, determine the orbital period of a satellite near Earth. The Moon is 60 R/b from the Earth's center and has an orbital period of 27.3 days. So here's our given information about the Moon, and we want to find the period of a satellite that just is skimming the surface of the Earth. I know, not very practical, but you'll see on the next slide why we're doing this. So if that's the case, the distance from the center of the Earth is just one Earth radius. We set up Kepler here. Here's the Moon's information. Here's our satellite's information. We solve for the period of the satellite, and we group the cube terms over here, and then we substitute in our variables. We have the period of the Moon is 27.3 days, and that's squared. And then we have 1 Earth radius over 60 Earth radius, and we need to cube that. Well, we cancel out the Earth's radius. We get 1 over 216,000. So our period now is squared. We'd like to take the square root of both sides, so we just get the period here. So it's 27.3 days times the square root of 1 over 216,000. Carry out the math, and then convert it to minutes. Okay? So in minutes, it's 84.6 minutes, right? There's how many minutes in a day? Well, let's see, one day, right? There's 24 hours. So we put 24 hours up here. Here's one day. And each hour is, I've kind of run out of room here, but it's 3,600 minutes. When you do that conversion, you find 84.6 minutes. A satellite orbiting at the surface of Earth would have an orbital period of about 85 minutes. Since the space station is 250 miles or 400 kilometers above Earth, its period is a little longer at about 93 minutes. The farther you get away from the object that's being orbited, the longer the period is. All objects orbiting the Sun have the same ratio of t squared over r cubed, and that's 4 pi squared over g times the mass of the Earth. And by the way, this picture is no way close to scale. It's the same for all the planets, asteroids, comets, etc. orbiting the Sun. It only depends on the mass of the Sun. Once Cavendish had determined the value of g, it was possible to find the mass of the Sun from the orbital periods and radii of the orbiting objects. The same formula was used to find the mass of the Earth by measuring the period and distance for Earth's moon, the distance that the moon is from the Earth's center. That's why Cavendish's determination of g has been called weighing the Earth. With the formula, it's possible to determine the mass of any object that is being orbited, but not the mass of the orbiting object. We determine the mass of Jupiter, right? Here's Jupiter, by measuring the period and orbital radius of its moons. Here's a few of its moons there. The same was done for all planets with moons. That did not allow us to determine the mass of those moons, since the mass of the orbiting object, the moons, is not revealed by that analysis. More recently, powerful telescopes have allowed us to find exoplanets. Exoplanets are planets that are orbiting other stars. By finding their orbital periods and radii, we have been able to find the mass of those distant stars. From the orbital radii and periods of stars orbiting black holes, which are incredibly massive objects, we have determined their mass. Stellar black holes have masses up to about 10 times that of our Sun. Supermassive black holes are up to 1,000,000 times more massive than our Sun. Ultramassive black holes are up to 1,000,000,000 times more massive than our Sun. Kepler's third law made measuring those masses possible.